let's say your mixed strategy okay, so let's say your mixed strategy is really best response, and let's say your mixed strategy, that mixed strategies randomizes 2 actions or 3 actions, then all actions in your support of your strategy have to provide the same payoff. Okay? That's what's really going on in this lemma. This lemma captures that idea. Okay, so this game is a coordination game. So the 2 players, there are 2 players, player 1 and player 2, they like to coordinate with each other. They have to make the same decision. Okay? If both of them choose A, then both of them enjoy payoff equal to 2. And if both of them choose B, then payoffs are 1 and 1. Okay? But whenever they choose different actions, different decisions, payoffs are 0. Okay? So this is coordination game. They like to coordinate with each other. Okay, so this game has 3 Nash equilibrium. And I'm gonna solve you all these 3 Nash equilibria here. Okay, so first that AL is Nash equilibrium. Okay, why? So in order to show that AA is Nash equilibrium, we have to check there is no unilateral deviation, no profitable deviation. Okay, and by deviation we mean we have to consider all possible mixed strategies in principle, right? But thanks to our lemma 1, we only have to check whether there is profitable deviation in mixed strategy. Okay? Okay, so let's check whether AA is Nash equilibrium. So let's think about player 1 first. So player 1 chooses A in equilibrium. So there is only one possible deviation in pure strategy, which is B. Okay? And if player 1 deviates B, then the outcome will be BA. And in that case, player 1's payoff is 0. But equilibrium payoff was 2. So that deviation is not really profitable for player 1. So meaning that player 1 has no deviation, no profitable deviation in pure strategy. And thanks to our first lemma, that implies that player 1 has no profitable deviation in mixed strategies as well. Okay? So summing up, player 1 really has no profitable deviation. Player 2, basically the same, right? I mean, if player 2 deviates, payoff will be 0, so there is no profitable deviation. Okay? So here, what is important also here is, whenever we think about deviation, for example, let's say player 2 is thinking of whether deviation is a good idea or not. When she or he thinks that possibility, this guy does not really care about player 1, right? He only or she only cares his or her own payoff. Okay? Okay, so AA is Nash equilibrium. Similarly, you can check 1 and 1, BB, that is Nash equilibrium. Okay? Okay, so here is kind of quick comments about, okay, so here we define, if you look at the definition of Nash equilibrium, we say strategy profile is Nash equilibrium or not, right? So whenever I ask you what is Nash equilibrium, your answer has to be some strategy profile. Okay? So, but one of common mistake of students is, in this case, I ask whether what is Nash equilibrium for this case. So the answer I want you to hear is something like A and A or B and B. That's some kind of answers I like to hear. But one of common mistake is sometimes some students report equilibrium payoff instead of equilibrium strategy. So if you answer 2 and 2, I know that what you have in your mind is actually A and A. But that is unfortunately wrong answer. Okay? So why it has to be wrong answer? To see why it is wrong answer, think about the case where the other example where payoff from A and A is 1 and 1. In that case, if you answer, if your answer is 1 and 1, then I'm not really sure whether you think about this outcome or this outcome. Okay? So when if I ask you what is Nash equilibrium, you have to answer. Your answer has to be strategy profile. Okay? And for the same reason, your answer has, okay, and also it is also the other thing you have to distinguish is strategy profile and outcome of game. Okay? So if all players play pure strategies, then strategy profile and outcome, they are kind of, the same, right? Let's say, player 1 chooses, let's say, Nash equilibrium here is A and A, but when I say Nash equilibrium is A and A, by A here, what I really mean is pure strategy A instead of outcome A and A. Okay? Of course, in this example, two things sound exactly the same, but sometimes, especially if player 1 or player 2, one of players play mixed strategy, there is clear distinction between strategy profile and possible outcome. Okay? So actually, I'm going to show you that there is actually a Nash equilibrium such that all 4 outcomes can be the case with some probabilities. Okay? Okay, so we just have shown that AA is a Nash equilibrium and BB is another Nash equilibrium. There is also third Nash equilibrium here, such that 2 players randomize A and B. So sigma 1A, let's say player 1 is choosing A with probability 1/3, player 1 choosing B, then probability 2/3, and sigma 2A is similarly 1/3, sigma 2B is 2/3. So this is another Nash equilibrium. Okay, so let's check whether this is really Nash equilibrium or not. So let's put star here to emphasize this is equilibrium strategy. Okay, first of all, let's compute what is equilibrium strategies, equilibrium payoff for player 1. So given that both of them play A and B, both of them choose A and B with positive probabilities, all 4 outcomes can be the case with some probability. Okay? So first, A and A, it is the outcome of the game with probability equals to this term times this. With this probability, player 1 chooses A. With this probability, player 2 will choose A. So the outcome is A and A with this probability. In that case, player 1's payoff is A1, A, which is equals to 2. Okay? with probability, this probability outcome is AB, and payoff is AB. This is the equilibrium payoff. And we know these numbers, right? Payoffs. This is 2, this is equal to 0, this is equal to 0, this is equal to 1. Okay? And we also know what are these probabilities, right? So this is 1/3, 1/3. Okay? So 1/3 times 1/3, this is equal to 1/9. This is 0. I mean, we don't really care about this term because this is already 0. So this whole term is also 0 because payoff is 0. And this probability is 2/3 times 2/3, so this is 4/9. Okay? So the equilibrium payoff is equal to 2/9 plus 4/9, which is equal to 6/9, which is equal to 2/3. Okay? So payoff here is, equilibrium payoff is 2/3. And similarly, you can show that player 2's payoff in equilibrium, this candidate of equilibrium is also 2/3. Okay? Any question? Okay, so then we have to show that there is no profitable deviation, and because of due to our lemma 1, we really only have to consider pure strategy, right? Deviation in pure strategy. Raise everything. So this is equals to 2/3, we know that. And we like to show this is larger than this payoff. Okay, so this is the payoff when player 1 deviates to A. So we would like to show this inequality is true, and also this inequality is true. Okay? Okay, so what is the payoff here? If player 1 chooses A with probability 1, then still player 2 plays our candidate of equilibrium, right? Which means that player 2 will choose A with probability 1/3, B with probability 2/3, right? But in this case, if outcome is A and B, the payoff is 0. So expected payoff here, if player 1 chooses A for sure, then expected payoff is probability 1/3 times 2, which is equal to 2/3. And if you think about this payoff, okay, so here payoff is 0. Let's say player 1 chooses B for sure with probability 1. then payoff for this case is 0, and payoff for this case is 1, but BB happens with probability 2/3, because player 2 chooses B with probability 2/3. That's our candidate of equilibrium, right? Here. So payoff here is also 2/3. Okay? So indeed, actually two payoffs are the same here, and these are also same payoffs. So player 1 really has no profitable deviation in pure strategy. Okay? Moreover, I mean, basically you can show that player 2 also has no profitable deviation exactly the same way. Okay, so this is actually, you might think this is kind of really coincidence. Why do we have to have the same payoff here and here, right? But this is not really coincidence actually. This is something we have to have. Remember that in order to justify randomization, you have to have the same payoff for each pure strategies, pure actions in the support of your strategies, right? So here, player 1 really randomize A and B, which means that player 1 has to be indifferent between A and B. Okay? So player 1's payoff from A has to be equal to payoff from B. Okay? And that also means that any randomization actually have to provide the same payoff. Okay? So especially equilibrium randomization has to provide the same payoff. 2/3. So player 1 is actually totally indifferent between any action, any strategy. Okay? What is really important here is, okay, so player 1 is indifferent between any strategies, okay? Indifferent between A and B, also indifferent between any possible mixed strategies. Any mixed strategies give the same payoff to player 1. However, it's kind of really, it's maybe a little bit tricky to some of you, but here what I want to see is, even if player 1 is just totally indifferent between any strategies, in equilibrium, player 1 has to play this statistic randomization. Because otherwise, player 2's randomization cannot be justified. If player 1 chooses A with probability slightly larger than 1/3, for example, then okay, let's say player 1 plays A, chooses A with probability 1/3 plus some small number epsilon. Then player 2 will immediately find that A is player 2's only best response. Okay? So my point is that even if player 1 is indifferent, player 1's any strategy is best response to player 2's equilibrium strategies. Player 1 has to choose this specific randomization. Otherwise, player 2's randomization is not justified. Okay? So it's kind of, okay, so let's come back to our Ross-Ritter sandpaper. So because, it's kind of easier to understand with that example because, that game is familiar to all of you. Your play in Ross-Ritter sandpaper is equal randomization, right? 1/3 and 1/3 to 1/3, right? And you don't, okay, and then given that your opponent is also playing 1/3 and 1/3 to 1/3, you are actually indifferent between all three actions, right? Given that your opponent is randomizing, there is no real difference between any choices actually in terms of winning strategy or in terms of payoff, right? However, you already know that even if you are indifferent, you have to use exactly randomization 1/3 and 1/3 and 1/3. Because as soon as you choose rock with slightly higher probability, your opponent will see actually paper is her best response. Okay? So we have same idea, you can see the same idea here. Even if player 1 is totally indifferent between any actions, he has to choose this specific randomization. Otherwise, player 2 will find, this equilibrium strategy is not real for player 2. Okay? Let me have just 5 more minutes. Actually, using that idea, we can show that there are only 3 Nash equilibria for this case. Okay, so remember, we identified 3 Nash equilibria. AA, okay, so that's equilibrium 1. BB, that's equilibrium 2. And mixed strategy equilibrium, we just found out from the board. Okay? And we will show that there are no other Nash equilibria. So these Nash equilibria are the only Nash equilibria for this case. Okay? So there is no other Nash equilibria. How can we show that? First of all, let's try to identify all Nash equilibria in pure strategy. Okay? So there are only 4 possibilities, right? So it's kind of easy to figure out what is all possible Nash equilibria in pure strategies. AA is Nash equilibrium. We just checked that. And we also just saw that BB is Nash equilibrium. But AB is not a Nash equilibrium because both players have profitable deviation, right? If player 1 deviates to B, then payoff will be 1 instead of equilibrium payoff 0. So AB is not a Nash equilibrium. And BA is also not a Nash equilibrium. Okay? So there are only 2 Nash equilibria in pure strategy. So that's step 1. And step 2, let's check if there is any mixed strategy equilibrium. In particular, let's try to find out if there is any mixed strategy, if there is any Nash equilibrium such that player 1 randomizes. Okay? So we are looking for now if there is any Nash equilibrium such that player 1 randomizes both actions, A and B. In order to that kind of Nash equilibrium to exist, player 1 has to be indifferent between 2 actions. Right? Player 2, in order to justify player 1's randomization, player 1's payoff from A has to be equal to player 1's payoff from B. Okay? Then what is player 1's payoff from A? That is equal to, with this probability, outcome will be A and A. And payoff will be this one. But we know that is 2. Okay? And if outcome is A and B, payoff will be 0. If outcome is B and A, payoff is also 0. And payoff is positive only if outcome is B and B. And that's the case with this probability. And that case, payoff is 1. Okay? So that is payoff of player 1 if this guy plays A. Okay? So this is the I'm sorry. So if player 1 chooses A, outcome is either AA or A and B, right? And outcome is AA with this probability. And for the other case, payoff is 0. Sorry. Okay? Okay, so then what if player 1 chooses B? Then outcome is either BA or BB. But in the first case, payoff is 0. In the second case, payoff will be BB, which is equal to 1. But we know that payoff that is the case with this probability. Okay? Okay, so remember that we are looking for a Nash equilibrium such that player 1 randomizes. Okay? So if player 1 randomizes, 2 payoff has to be equal. Right? Otherwise, randomization is never justified. If player 1 finds randomization, any randomization is best response, it has to be the case that the first payoff has to be equal to the second payoff. Okay? And that is the case only if, okay, so that means sigma 2a is equal to sigma 2, I'm sorry, here we have sigma 2 b, right? So here, this one, and on the right hand side, this one. And that is the case only if sigma 2a is 1/3. And sigma 2b is 2/3. Okay? Okay, that's not the end. We have to do one more thing. Okay, so what we just have shown is, in order to justify player 1's randomization, player 2 also has to randomize. Okay? In order to justify player 1's randomization, we have to have player 2 place this randomization. Right? Then we also have to justify player 2's randomization. Okay? And then we'll show that we have to have the same probability for player 1. Okay? What we have shown is, remember, we were looking for if there is Nash equilibrium such that player 1 randomizes. Okay? And what we have shown is, in order to, if that is the case, if there is any Nash equilibrium such that player 1 randomizes, we have shown that player 2 is also randomizes. And to justify that, player 1 also has to randomize, right? And with this specific probability. And that probability is exactly probability we have checked to be Nash equilibrium. Okay, so then our conclusion is, okay, indeed, there is Nash equilibrium such that player 1 randomizes. And all those random, if there is any that kinds of Nash equilibrium, that has to be this Nash equilibrium. Okay? So that shows that there are only 3 Nash equilibria: AA, BB, and this specific randomization, Nash equilibrium in mixed strategy. I was a little bit fast at the very end of this lecture today, but I'm gonna, of course, I'm gonna repeat this example again next week, so do not worry too much about it. It was too fast for you. And next week, I'm gonna finish